Okay. Now we'll be discussing about ALU, that is nothing but arithmetic logical unit. How ALU is going to design, that is all we'll see here. See, arithmetic logical unit, that means how arithmetic operations will be performed. Arithmetic means like a plus b, okay, like, or else a plus b, a plus b plus 1, a minus b, all these arithmetic operations, how all arithmetic operations will be performed. At the same time, logical operations, how logical operations can be performed. Like, what are the logical operations? A XOR b, a XNOR of b, okay. At the same time, a is greater than b or a is less than b. All the logical operations, how it is going to perform, that all will be seeing here, okay. See, suppose it is like a naught to a3, that is a is of 4 bit, like you are designing a 4 bit full adder. A is of 4 bits and b is of 4 bits. You want to design 4 bit full adder, it will take a 4 bits and b 4 bits, and that will be given to 1 bit ALU. 1 bit ALU will be taking a naught, b naught and c naught, okay, taking selection lines as S0 and S1, providing F0 as your output, okay. Also similarly, but in 1 bit ALU, how it is going to be there? See, this is your 4 bit ALU. What in 1 bit ALU, how it is going to be there? In 1 bit ALU, you will find this one. See, in 1 bit ALU, you have 4:1 mux, okay. See, a into b, that is a into b, you will be getting a or b. Here you will be performing a XOR b. Here you will be performing addition operation. Addition operation means a plus b, that is addition, that is sum, whatever the sum, a XOR b. Your add, so that is nothing but if you add 3 bits, what will be your 3 bits? A XOR b XOR c naught. So whatever that sum will be providing. So depending upon your selection lines, if at all in selection line is 0 0, if at all selection line is 0 0, what happens? Whatever your input a into b, you will be getting your output. So you are performing AND operation, okay. You are performing AND operation, like a into b you are getting, okay. At the same time, if at all selection input is equivalent to 0 1, if it is 0 1, whatever a plus b you will be doing, that means addition operation, okay. Addition operation you are performing a XOR b, logical operation. So depending upon your 1 0 1 1, if it is 1 1, it is going to be acting as an adder, full adder, okay, like that. So in ALU you are going to design arithmetic operation as well as logical operations simultaneously. So depending upon your selection lines, you can take your output. See, there are 3 selection lines as well as carry in, and there are 3 bits. See, the internal circuitry we have seen, this is your ICs. These are 74 by 381 and 74 by 382 ICs, okay. These are 4 bit ALUs. Whatever that circuit you have seen, that IC, this is the IC looks like, where there are 3 selection lines, S0 to S2, as well as 4 bits. At the same time you have G and P, these are active low signals, and F0 to F3. Similarly this also, that means depending upon your CIN and the selection lines, you are going to perform which operation has to perform. That means these selection lines will decide which operation has to perform and what will be your outputs, whether it has to perform arithmetic operations or logical operations will be decided by these 3 selection lines. Similarly here also, see, ALU is a combinational circuit that can perform several arithmetic and logical operations on a pair of b bit operands. That means it is going to perform arithmetic as well as logical operations. Here it is going to take, it is taking 3 bits as well as selection line, and depending upon your m value, see here in this IC, depending upon your m value, it is going to decide whether it is going to do logical operations. See, in order to select which gate, it is doing with the help of selection gates, but with the help of m input, it can able to decide what has to do with that operation performed by 74 by 171 is selected by the m and selection inputs. How that means which operation has to be performed, it depends upon your m as well as selection inputs. That truth table I'll be showing it now. See, mainly whatever the m value, see now this is your truth table, or telling it what is the function has to be. See, this is your inputs, that means selection lines. All the selection lines you have seen there are 3 selection lines, 4 selection lines, S0 to S3, there are 4 selection lines. And again, if you see here m value, as they gave m value, if m is equivalent to 0, it performs arithmetic operations. If m is equivalent to 1, it performs logical operations. Logical operations in the sense, see here, a XOR with b complement, a plus b complement, or a XOR b, like that, a XOR b, a plus b, like that. It is going to a greater than b. Okay, a is less than b. All these logical operations can be performed when m is equivalent to 1. If at all m is equivalent to 0, it is going to perform arithmetic operations. See here, f is equivalent to, see what will be your f? That is a minus 1 plus c in. Okay, that means whatever the data a value minus 1 plus c in, depends upon your a value. It is going to perform arithmetic operations. Again, see that all like with the help of a, if you see here, that means depending upon your selection lines, it is going to, and m value, only depends upon selection lines and m value, it is going to perform either an arithmetic operation or logical operation. XOR and parity circuits. See, you from this truth table, you might be noting that if at all odd number of inputs in XOR truth table, if it is like odd number of ones, 0 1 and odd number of 1, odd number of ones you are getting output as 1. Okay, and again even number of ones 1. See, from XOR circuit can be also be used as a parity circuit. What is a parity circuit? What are parity circuits? XOR and parity circuits. That means whatever the data you are being transmitting. Suppose you want to transmit 1101. This is your data. This has to be transmitted. Okay, but at the transmitting end you will be having parity generator. Okay, at the transmitting side you have a parity generator. What it will be doing? It will add parity bit to this data. So let us assume that parity bit 1 is there. 1 is being added with this data and sent to the receiver. So at the receiving end you will be having a parity checker. Okay, parity checker. What it will be doing? It takes the data. Either it may be like odd parity generator or even parity generator. Okay, whether it may be odd parity generator or even parity generator. If at all, depends upon your parity generator, at the receiving end it will check. Okay, whether if it is an odd parity generator, odd number of ones are there, or even parity generator, even number of ones are there. So it will check the data again. So if at all it is like odd parity generator, suppose consider here it is an odd parity generator. So odd number of ones has to be there. So at the receiving end it will check whether whatever the data you have got, whatever the data you have got, it is having odd number of bits or not. If it is having odd number of bits, okay, then whatever the data you have transmitted you have got correct. If at all odd number of bits are not there, if any one bit has been changed, 1 1 0 1 1, something like this, something, so if any one bit has been changed, it resembles that there is an error. Okay, there is an error present in the data, like that. So that is the main applications of parity generators. If you see here, 0 and 1, 0 and 1, odd number of ones, XOR output is 1, 1 and 0, output is 1, that means odd number of ones it is providing 1. Okay, so it is also an example for parity circuits. Now we are using that only. See, these are like, this all represents your XOR gates only. See again here, see, whatever you are getting is I1 XOR with I2. Okay, again it is taking I3, again you will be getting like I1 XOR with I2 XOR with I3. Okay, so in order to find out odd parity generators, you are taking this circuit. Either you can consider this as a DICA chain, or you can consider, you see, number of stages has been increasing. If at all more number of bits, suppose like 20 number of inputs were there, there will be 20 stages will be there. So as if you want to get an output, it takes more amount of delay. So it can be overcome by the tree like structure, tree chain like structure, where all the input bits are kept to XOR gates simultaneously. Okay, the output of these two XOR gate will be given to one more XOR gate, like that. So that means the delay is being reduced. We'll consider, see, as you all know, like example I'll be considering X is of 7 bits, X is of 7 bits and Y is of 7 bits. Suppose I'm considering like 3 bits, right? 0 1 1 and 0 1 1. 0 1 1 in the sense 6 6, that means you are multiplying 6 with 6. Your answer should be like 12. So what you will be doing, first you will be taking, this is your X bits, that is X of 0, X of 1 and X of 2. This is your lowest significant bit, that is Y of 0, Y of 1 and Y of 2. Now what you will be doing, Y of 0 is multiplied with whole X term, like that. See, 0 with 0 0, 0 with 1 1, 0 with 1 0, like that. That means Y of 0 is multiplied with whole the term. Again next, Y of 1 is multiplied with whole X term, that 1 into 0 0, 1 into 1 1, 1 into 1 1. Similarly, again 1 is multiplied with whole term, that is 1 into 0 0, 1 into 1 1, 1 into 1 1. What you will be doing, you will be adding up, right? 0 0, 1 1 plus 1 is 0, 1 1 plus 1 is 0 1. This is what you are been doing in multiplications also. That means you see here, in this row you can find Y naught is being multiplied with whole X term, and again you are leaving this gap. Again here if you see, Y1 is multiplied with all X terms, again Y2 is multiplied with all X terms, and Y3 is multiplied with all X terms. Okay, similarly so on. How you will be getting P naught? P naught is nothing but your X naught into Y naught. How you will be getting P1 here? That means addition of these two terms will provide you P1. As similarly see here, this is your P naught. How you will be getting, adding up these two values, you will be getting your P1. This is your P1, this is your P naught, this is your P2. Adding up these three values will provide you this one. Similarly, P2 is nothing but addition of these 3 bits, like this. This is your normal multiplication operation as we do, right?